Practice problem number 4, this is Unit 4, Lesson 12, has students working with the equation to change degrees Celsius. So you're given degrees Celsius and you change that temperature, that measurement, to degrees Fahrenheit. So the temperature in degrees Fahrenheit is related to the temperature in degrees Celsius by this equation. And what we say is that this equation is the degrees in Fahrenheit are written in terms of degrees Celsius. So this degrees Fahrenheit are written in these terms of degrees Celsius. So 9/5, whatever the degree Celsius is, plus 32. So this equation is written in terms of degrees Celsius, and what we're going to do is rewrite it in terms of degrees Fahrenheit. So that just means that you're going to have Celsius equals some expression over here that is the measurement in degrees Fahrenheit. But first notice that from this equation, you can tell that a degree Fahrenheit is 9/5 a degree Celsius. So a degree Fahrenheit is a measurement that's larger than a degree Celsius by 9/5. So if I divide a degree Celsius into fifths, so 1, 2, 3, 4, 5, a degree Fahrenheit is 9 of those fifths. Well, this is 5, 6, 7, 8, 9. So the relationship between a degree Celsius and a degree Fahrenheit is that Fahrenheit is larger by 9/5. And then to get to the degrees Fahrenheit, you have to add 32. This is the y-intercept. So it starts out 32 degrees ahead, and you have to add these 32 degrees to change degrees Celsius to degrees Fahrenheit. Now, what if we rewrite it in terms of degrees Fahrenheit? This is written in degrees Celsius. I'm going to rewrite it in terms of degrees Fahrenheit. So that means I have to move everything over to the other side of the equation and rewrite this as Celsius equals something. So to do that, I'm going to add a negative 32 to both sides. So that 32 degrees goes away here, and it ends up on this side as a negative 32 degrees. And I'm left with 9/5 degrees Celsius equals whatever the amount is written in terms of Fahrenheit. Okay, so now I have to get rid of that 9/5. I'm going to do that by multiplying by the multiplicative inverse, which is 5/9. So 5/9 times 9/5, this becomes 1, so this goes away. And so you can do this one of two ways. I can either write it as 5/9 times this whole expression here, Fahrenheit plus a negative 32 degrees, or I can write it as 5/9 times each term. So 5/9 times Fahrenheit and 5/9 times a negative 32. So if I want to figure out what the y-intercept is when the equation is written in terms of Fahrenheit now. So now this is Celsius written in terms of Fahrenheit. I can use the distributive property to figure out that it's 5/9 degrees Fahrenheit. So notice that a degree Celsius now is 5/9. It's smaller than a degree Fahrenheit. So if I divide that degree Fahrenheit into 9 equal parts, a degree Celsius is 5 of those 9 parts. It's 5/9 the size of a degree Fahrenheit. And the y-intercept is at a negative 17 7/9. So to rewrite this properly, it's Celsius is equal to 5/9 a degree Fahrenheit. So a degree Celsius is smaller than a degree Fahrenheit. And then you have to add a negative 17 7/9. So this is the y-intercept when the equation is written in terms of Fahrenheit, so that Celsius equals whatever you're given in terms of Fahrenheit. In part A, you're going to work with the equation that's written in terms of degrees Celsius because you're given degrees Celsius. So 50 degrees Celsius, and you're going to use that equation to calculate what the temperature is in degrees Fahrenheit. So now remember, a degree Fahrenheit is larger than a degree Celsius. It's 9/5 a degree Celsius. So if you're starting out with 50 degrees, you're going to multiply this 50 degrees by 9/5, because a degree Fahrenheit is 9/5 times that, or 9/5 larger. Well, 9/5 times 50, 50 divided by 5 is 10, and 9 times 10 is 90. And then you're going to add 32 degrees to that 90, and your answer will be 122 degrees Fahrenheit. So let's go through the algebra. Again, you're given degrees Celsius, so you're going to use this formula written in terms of degrees Celsius. So now it's 9/5 times that 50 degrees, so it's going to get larger. So 9/5 times 5 times 10, or 50. You can factor out the 5s. You're left with 9 times 10 is 90, and you add that 32 there, and you get 122 degrees Fahrenheit. The highest temperature ever recorded is actually in Death Valley, California, on July 10th, 1913, measured 56 7/10 degrees Celsius, which equals, now you could use this formula to figure this out, equals 134 1/10 degrees Fahrenheit. So it's 9/5 times this temperature. It's kind of hard to do. Use a calculator to figure that out, and then add 32 to that, and that gets you up to 134 1/10 degrees. Now, if you're going to add 32 to that, that means that 9/5 of this has to be 102 degrees and 1/10, because then you're going to add 32 to that to get to 134 degrees. Now, it's a good idea to graph these equations and look at these answers, because it deepens your understanding of the math. It builds that relationship between the graph, the equation, the y-intercept, all of the slope, all of those things. So this is a graph. So the equation, or the formula, is degrees Fahrenheit. That's on the y-axis. You're going to figure out what that is given degrees Celsius, and that's on the x-axis. So it's 9/5 degrees Celsius, so the slope is 9/5. So for every 5 units along the x-axis, it's going to go up 9 units along the y-axis. So for every 5 units Celsius, Fahrenheit is going to be 9 units. So if I go out 25 units, then I have to go up, that's 5 times 5, then I have to go up 45 units, which is 9 times 5, to stay on this same graph. Remember that the y-intercept is at 32. So this is 5 units, and this goes up 9 units. So you see it's a little bit beyond there. So this is 5 right there, and then another 4 right here. You have to just kind of guess a little bit. A little bit easier to see 25, and this goes up 45. So you can count. So this is a little bit past, if I count by 5s, 5, 10, 15, 20, 25, 30, 35, 40, 45. And then I go a little bit past that. It's like going a little bit past this down here, and you get to this line, the graph. Now it goes off the page up here. So if you go out degrees Celsius out to this value, 50 degrees Celsius, and then you go up to where it intersects, it's going to intersect way up here at 122 degrees Fahrenheit. It does go off the page, but you can see that this is 110. So as this is approaching this line, they will intersect at 122 degrees. For part B, you're given the temperature in Fahrenheit, so negative 60 degrees Fahrenheit, and you're supposed to figure out what that temperature is in degrees Celsius. Now you can use either form of the equation that you want. The authors seem to push you towards using this form of the equation. So if you're given 60 degrees Fahrenheit, you just plug in 60 degrees here and you solve for degrees Celsius. Or you could use this form of the equation. Actually, I use this form right here, in which you plug in the 60 degrees Fahrenheit here and then go through and solve, and you get the degrees Celsius. Either way, you're going to do the same calculations. So if you plug in 60 degrees here, you're going to subtract this 32. So plug in 60 degrees here, you're going to subtract this 32, same thing. And up here, you can end up multiplying by 5/9. And down here, you end up multiplying by 5/9. So the calculations are the same. I just think it makes more sense to use this form of the equation because you're given degrees Fahrenheit. You're given degrees Fahrenheit, and you're going to calculate degrees Celsius. So this is that formula written in terms of Fahrenheit. Those are the degrees you're given, and you're going to calculate how much that is in degrees Celsius. So it's a negative 60 degrees plus a negative 32 degrees. That's a negative 92. So 5/9 of 92. And so one way of approaching that without using a calculator is just to split the 92 into a number that's a multiple of 9, and then whatever's left over. So 90 is a multiple of 9, so I can rewrite 92, or negative 92, as a negative 90 plus this negative 2. And I'm going to distribute the 5/9 to that. So it's 5/9 times a negative 90 plus 5/9 times negative 2. Well, negative 90 divided by 9 is 10. So that's a negative 10. 5 times negative 10 is negative 50. And then over here, negative 2 times 5 is negative 10 again. So this is a negative 10/9. That's a negative 1 and 1/9. So this is negative 50 here. So 5/9 times 9 times negative 10. I factored out the 9 and then multiplied what was left by 5 times negative 10. So that's the negative 50. And over here, this is a negative 10/9, which is negative 1 and 1/9. Add those together. And without using a calculator, and you can almost do this in your head, a little bit of practice, you can do this in your head. You get an answer of a negative 51 and 1/9 degrees Celsius. Now it is useful to graph this once again. I showed you this before, but I did not go through how I got negative 17 and 7/9. So let's do that just for a moment. So if I distribute this 5/9 to degrees Fahrenheit, so it's 5/9 times degrees Fahrenheit plus 5/9 times a negative 32. So 5/9 times degrees Fahrenheit. So 5 times negative 32 is a negative 160. And I want to divide that by 9. A little bit hard to see right away. So again, split this 160 degrees, or 160, into a multiple of 9 and whatever's left over. Well, I know that 9 times 10 is 90. So 90 is a multiple of 9. And I know I can include 45 more units. It's going to get me to 135. So I know that 135 is a multiple of 9 because it's 90 plus 45. So factor out the 9, and you get 9 times 15. So I'm going to rewrite this negative 135 as 9 times a negative 15. And what's left over is a negative 25/9. Well, 25/9, 2 times 9 is 18. So that's 2 times, and then 7/9 are left over. So this is a negative 2 and 7/9. And all I'm trying to show you here is that you don't always have to revert to using a calculator. You can do much of this in your head or on a piece of paper, just thinking about multiples. So you end up with a negative 15 here. These 9s cancel, plus a negative 2 and 7/9. Add them together, and you get that negative 17 and 7/9. You want to make that calculation because this is the y-intercept. This is the slope, 5/9 of times the degrees Fahrenheit. So remember that degrees Celsius are smaller than degrees Fahrenheit. Actually, they're 5/9 the degrees Fahrenheit. So if you go 9 units along the x-axis, so degrees Fahrenheit, you're going to go up 5 units along the y-axis, which is degrees Celsius. So this degrees Celsius is 5/9 of the degrees Fahrenheit. So this is a little slope triangle here, and so you want to extend this side of that slope triangle. A little bit hard to do. And so, but you do know one more point on this line. You do know that this point right here is negative 60 degrees Fahrenheit, and you calculate that as being a negative 51 and 1/9 degrees Celsius. So you can place that point right there and just check how well you drew this line. And the coldest recorded temperature on the planet is a negative 128 and 6/10 degrees Fahrenheit, which is equal to a negative 89 and 2/10 degrees Celsius in Antarctica on July 21st, 1983. Now notice that the hottest temperature was July, it was 1910. I'd have to look back, but it was July. But that was in the northern hemisphere. And the coldest temperature is also in July, but this is in the southern hemisphere when it's cold during July. And notice further that negative 128 degrees and 6/10, you're going to figure out what 5/9 of that is. Well, 5/9 is a little bit more than half. Now remember, you have to add a negative 32 degrees to this. So you add a negative 128 plus a negative 32, that is a negative 160 degrees. And 5/9 is a little bit more than half. Well, half of 160 is 80. A little bit more than half is going to get you to this very close to negative 90 degrees. Hopefully that makes sense. Useful to go through those calculations, those mental checks of how these numbers are being calculated. Part C was interesting to me in that I did not realize that there was one temperature where the degrees Fahrenheit and the degrees Celsius were equal. The expression or the equation for that relationship is that Celsius equals Fahrenheit. And so the directions say use the expression from the equation where Fahrenheit, degrees Fahrenheit, is expressed in terms of degrees Celsius to solve for this temperature. So what they mean there is to use this equation, this formula, where Fahrenheit is written in terms of degrees Celsius. Well, that means that Fahrenheit is equal to this expression, and the degrees Fahrenheit is also equal to this expression. So I'm just switching this around. So I want Fahrenheit on the left side of both equations. They are equal, which means that the right side is also equal to each other. So now we can rewrite this equation as degrees Celsius equals 9/5 degrees Celsius plus 32. So now we're just going to go ahead and solve for degrees Celsius. I'm going to rewrite this 1 here as 5/5 because I'm going to add a negative 9/5 Celsius to this side. I add a negative 9/5 Celsius here. This goes away. Add a negative 9/5 Celsius to the left side, and you're left with that equal to 32. Well, a negative 9/5 plus a positive 5/5 is equal to a negative 4/5. So now you're left with a negative 4/5 degrees Celsius is equal to 32. Multiply through by negative 5/4, which is the multiplicative inverse of a negative 4/5. This becomes 1, essentially goes away, and you're left with a negative 5/4 times 32. Rewrite the 32 as 4 times 8 so that you can factor out or cancel out the 4's. And you're left with 5 times 8 that equals a negative 40 degrees. So at a negative 40 degrees, both Celsius and Fahrenheit are the same. Now this really shouldn't have been a surprise, and you see in the graphs that as you move towards lower and lower temperatures, the difference between degrees Fahrenheit and degrees Celsius gets closer. But we know that 0 degrees Celsius, so down here, 0 degrees Celsius is equal to 32 degrees Fahrenheit. So these are separated by 32 degrees. And we know that boiling is at 100 degrees Celsius, so way out here to the right. And it's the same as 212 degrees Fahrenheit. So that's a 112 degree difference. And we just saw that a negative 60 degrees Fahrenheit is very close to a negative 50 degrees Celsius. So those are only 10 degrees apart. So they seem to be getting closer to each other as you go towards lower and lower temperatures. But if you take this graph here and you place on that same graph the graph of Fahrenheit equals Celsius, and where those, that becomes a system of equations, where those graphs intersect is the solution to that system of equations. That's the point behind this entire lesson. So I have to expand this out a little bit because we have to get to negative 40 degrees Celsius and also negative 40 degrees Fahrenheit. So I'm going to expand this out a little bit. And so now I have negative 40 degrees Celsius on the graph and a negative 40 degrees Fahrenheit. This over here is what we just got done doing. This is figuring out that the Celsius is equal to negative 40 degrees and Celsius is equal to Fahrenheit at a negative 40 degrees. So you just add this graph, degrees Fahrenheit equals degrees Celsius. That means that the y-intercept is 0 and the slope is 1. So you go over negative 1, down negative 1, over negative 1, down negative 1. The same as going over 1 to the right and up 1 on the y-axis or on degrees Fahrenheit. So you just extend this graph out, and where do these two graphs intersect? That's the solution to both equations or to the system of equations, and it intersects at negative 40 degrees Celsius and negative 40 degrees Fahrenheit. So it makes sense. Now if you flip this around, and now you look at this graph in terms of Celsius in terms of Fahrenheit. So now Fahrenheit is going to be on the x-axis. A moment ago, Celsius was on the x-axis because this was written in terms of degrees Celsius. But if you rewrite this expression or this equation in terms of degrees Fahrenheit, so now Celsius is equal to degrees Fahrenheit. Go through, I showed you this before, the y-intercept is a negative 17 and 7/9 degrees, and the slope is 5/9. So every 9 degrees to the left is 5 degrees down, 9 degrees to the left, 5 degrees down, and so on. Now add to this graph the graph of Celsius equals Fahrenheit. So Celsius is equal to Fahrenheit. So that's one equation. The second equation is the same equation here. Celsius equal to 5/9 times Fahrenheit minus 32 degrees. So add this graph, Celsius equal to degrees Fahrenheit, and where do they intersect? Remember that slope is 1, so it's a negative 1, negative 1, negative 1, negative 1. Where do they intersect? They intersect at negative 40 degrees Fahrenheit and negative 40 degrees Celsius. And this is what we looked at just a moment ago, that a negative 60 degrees Fahrenheit is equal to a negative 51 1/9 degrees Celsius. And so notice this has gone past this intersection. So now this is starting to be a larger and larger difference as you go past. It gets closer and closer and closer degrees Fahrenheit to degrees Celsius until they're the same at this point, and then you go past that point, now they're getting farther and farther apart again. Now it shouldn't have been a surprise. It turns out that if you take any linear equation, the graph of any linear equation, and you add to it the graph of the units along the x-axis are equal to the units along the y-axis, they will always intersect. So here's an example of just a graph of a linear equation. Whatever this is the graph of where the units along the x-axis are equal to the units along the y-axis. Draw that graph and they intersect. That is the solution. That is the point where the number of units along the x-axis is equal to the number of units along the y-axis, and at the same time it satisfies whatever this relationship is. Well, I took this graph from an earlier problem. This is from problem number 2, in which we looked at the pounds of broccoli compared to the pounds of zucchini. And if you remember, this line was the line on which each combination was equal to $17. So whatever combination of broccoli and zucchini was purchased, that combination was equal to $17. So let's figure out where that is, where when you purchase the same number of pounds of broccoli and the same number of pounds of zucchini, what is that value? And at the same time, it's equal to $17. Well, it's almost 5 pounds, a little bit less than 5 pounds of zucchini, and the same as a little bit less than 5 pounds of broccoli. So how do you figure out exactly what that is? Well, this is the equation that we used before. This is the $1.50 for each pound of zucchini and $2 for each pound of broccoli. And then you get this into the y-intercept form, and you end up with a slope of -3/4. So if you go from here, slope of -3/4 means I go 4 units to the right along the x-axis. I'm going to go down 3 units. Remember, that's 2 grid lines in this case. This is 1 unit, 2 units, 3 units. So that's a slope of a -3/4, and the y-intercept is up here off the graph at a positive 8.5. So what is this value where they intersect? Well, I'm going to add to this the second equation, which is right here. So y is equal to x. So this is one equation. This is the other equation. So now I can set these two expressions equal to each other. So x is equal to -3/4 x plus 8.5. Solve for x. Just work through this and solve for x. And you want to leave this as a fraction. So you're going to get down to a kind of a tough fraction to deal with. It's 4/7 times 17/2. I could have simplified this right now in factoring out the 2 here and the 2 here. So I could have had 34/7, but I multiplied them out. I got 68/14. I want to separate this out into a multiple of 14, and then what's left over? Well, 4 times 14 is 56. So I can take 56 of this 68 and rewrite that as 56/14 plus 12/14 is what's left over. This is equal to 4, and we know that the answer is more than 4 pounds but less than 5 pounds, and it's just less than 5 pounds. This fraction here simplifies to 6/7. So at 4 and 6/7 pounds of both zucchini and broccoli, they will cost together $17. Well, let's check that out. If I change it to a decimal value, it's 4 and 86/100 pounds. You don't want to do that though, because now this is not an exact value. This fraction is exact. This fraction, or this decimal, goes on forever and ever. So it's not exact once you round it off. So leave it as this fraction and use that value to see if the answer is in fact $17. So I'm going to take 4 and 6/7 pounds of each and plug them into this equation. So this is $1.50 times 4 and 6/7 pounds for the broccoli. That was the zucchini. And $2 times 4 and 6/7 pounds for the broccoli. I'm going to use the distributive property. I'm going to change this to 3/2. 3/2 times this 4 right here, and 3/2 times this 6/7. Make it easier to deal with that fraction. And at the same time, 2 times this 4 right here, and 2 times this 6/7 right here. So now we just go through the arithmetic. 3/2 of 4. 4 divided by 2 is 2. 2 times 3 is 6. And 3/2 times 6/7. 6 divided by 2 is 3. 3 times 3 is 9. So that's going to give me 9/7. 2 times 4 is 8. And 2 times 6/7 is equal to 12/7. So keep these as a fraction. Just hang in there. It will become easier in a moment. 8 plus 6 is 14. 9 plus 12 is 21. So this is 21/7. Well, 21/7 is equal to 3. And you add these two together. 14 plus 3 is equal to that $17. So it does work. So you go back to here. This point is where the number of pounds of zucchini and the number of pounds of broccoli are equal, and that's 4 and 6/7 pounds. And at the same time, that combination costs $17. So this is true for any linear relationship. So the graph of any linear equation, wherever that is in the coordinate grid, you can then draw a graph of y equals x And wherever that intersects, that will be that relationship of equal units for y and x and satisfies whatever that linear relationship is at the same time.